2.71828. This number has no obvious pattern by the looks of it, or no clean story behind it at first glance. However, the strange thing is that it keeps turning up, and in completely unrelated circumstances. You see it in compound interest, for example. You see it in population growth, radioactive decay, the normal distribution that describes random variation across nature. The exact same number every single time, and no one even put it there. This is slightly intriguing to me, and it's worth focusing all my attention on, and yours too, because when the same constant appears in finance, biology and physics, which are fields that were developed independently by different people to describe completely different things, that's not a coincidence. That's telling us something deeper. So the question is, what are we actually being told by this number? Well, for me and most mathematicians, the first instinct is to look for a geometric explanation. And that's usually how these things go. Pi has one and is beautiful, as well as simple. The circumference of a circle divided by its diameter. Wherever circles appear in nature, pi follows. That makes perfect sense. But what's E's version of this? And this is where it gets kind of interesting, because there actually isn't one. At least not in any clean geometric sense. And you can't point to a shape and say E is that ratio. It doesn't come out of geometry the way pi does. So it must be coming from somewhere else. Okay, I'll start with the simplest possible situation. You have $1, or pound if you're like me and British. You put it somewhere that pays 100% interest per year. After a year, you have $2. Fine. But what if the bank compounds it? Instead of once a year, they do it twice a year. You get 50% after 6 months, and then 50% on the new total. If you work it out, you end up with $2.25 instead of just $2. Do it 4 times a year, quarterly, and you get $2.44. Monthly, $2.61, daily $2.71, and you get the drill. It just keeps going and going. You're watching it convert to something, and that something is Euler's number, E. What's happening here is that as you compound more and more frequently, the benefit of each compounding period gets smaller and smaller, but you're doing it more and more often. Those two things balance out, and they balance out at exactly Euler's number. And it's not a coincidence that it shows up in finance. The mathematics of growth, anything that grows continuously, proportionally, on itself, pulls this number out almost inevitably. Here's a different angle on the same idea, and this one I find genuinely strange. Is there a function whose slope at every point equals its own height? Think about what that means. At x equals 0, the height is some value, and the slope, the rate of change, is exactly that same value at every single point. For most functions, like a quadratic function or a linear function, slope and height are different things. They change in completely different ways as you move along the curve. The idea that they'd be identical everywhere seems almost too strict, way too specific. But there is exactly one function that does this, and that's e to the x. Look here on the graph. Pick a point. The height of the curve there and the steepness of the tangent at that point are the same number. Move it to a different point, it's still the same, nothing has changed. The function and its own derivative are identical. That's the defining property of E. Not a geometric ratio, not a pattern in digits, a function that its own rate of change. What's remarkable about Euler's number is that you can actually build this function from scratch, just from that one rule. If f prime equals f and f of 0 equals 1, what can we figure out? Well, f of 0 is 1, that's our starting point. But if the slope has to equal the value, then the slope at 0 is also 1. So we add a linear term, 1 plus x. But now the slope of that has changed. To match that, we need to add a correction. It turns out that the correction is x squared over 2. And then that changes things again. Another correction, x cubed over 6. Each time you add a term, the approximation gets closer to the true curve. To put it simply, you're essentially chasing your own tail, but the chase converges. If you add infinitely many of these terms, you will land exactly on e to the x. The function, is literally its own correction mechanism, and it literally builds itself. Remarkable. So back to the initial question, why does this number appear in biology and physics and statistics and many other things? Well, it's because in all of those fields, at some point, they describe a situation where rate of change of something depends on how much of that thing already exists. More people means more births. More radioactive atoms means more decay events. More money in an account means more interest. The mathematical statement of that is simple. The rate of change of y equals some constant k times y itself. And when you solve that equation, when you find the function that actually satisfies it, the number always involves Euler's number. Not because anyone designed it that way, but because that's the shape of the solution. The universe keeps setting up problems of this form, and E keeps being the answer. So Euler's number isn't just a number that someone stumbled across and then noticed was everywhere. It's the answer to a question. What function grows at a rate equal to its own size? That question has exactly one answer, and the number at heart of that answer is E. The reason it shows up in compound interest, population growth, radioactive decay, and everything else mentioned before is because all of those are asking, in different words, the same underlying question. That's what makes E different from something like pi. Pi is a geometric constant. E is something deeper. It's baked into the mathematics of change itself. One more thing before we finish though. There is an equation that has always struck me as slightly unreasonable. E to the power of I pi plus 1 equals 0. 5 numbers that were developed entirely separately. E being the base of natural growth, I being the imaginary unit from algebra, pi the ratio from geometry, and the two most fundamental numbers in arithmetic, 0 and 1. All connected in a single exact equation. Why? Why would the number that governs growth be related to the geometry of circles and the square root of -1? That's not obvious, and honestly, following the answer to that question is where imaginary numbers become unavoidable. The thing that Euler's number is really pointing at is this. The universe seems to have a preferred shape for growth. Anything that grows or decays in proportion to its current size, and that's a lot of things, follows Euler's number. It's not arbitrary, it's forced on us by the structure of calculus, by what it means for something to change continuously. And the fact that it then connects to pi, to imaginary numbers, to the geometry of rotation in the complex plane, that shouldn't work, but it does, completely. That's what makes this worth understanding, not as a piece of trivia, but as a glimpse of how deeply the same ideas run through very different parts of mathematics.